Good evening, everyone. My name is Bo Lauder, and I'm the principal of the school, and we are delighted that you are here tonight for the Art of Teaching lecture by Fred Schubert. When this series came into being, it was endowed actually by members of the school administration who so prized the work of our faculty that we wanted to find a venue and a way to bring their work outside of the classroom so other people who don't have the privilege of sitting in our classrooms could see the brilliant work that our teachers do. Daphne Taylor, head of our art department, was our first recipient, and Maria Fahey, chair of the English department, was our second recipient. And our third recipient is Fred, here in this 225th year that the school has been in existence. It's a real pleasure to have you here in Friends Seminary and to be part of this lecture, which is part of an ongoing set of things that we're doing to celebrate the school's milestone. So welcome. Fred has actually taught here at Friends Seminary since 2001. He was chair of the department, he taught advanced chemistry, he taught chemistry, and his signature course, History of Science and Knowledge. Fred has a bachelor's degree in chemistry from SUNY Stony Brook, and a master's and a Ph.D. from Adelphi. He is the holder of over 20 patents, which I did not realize until I took a look at his resume today in preparation for this introduction. He was also, prior to coming to Friends, a visiting scientist at Brookhaven National Labs. He's also a published scholar. And I thought this title was particularly reflective of Fred's level of intellectual engagement in his field. This is one of his articles. Important sampling and histogrammic representations of reactivity functions and product distributions in Monte Carlo quasi-classical trajectory calculations. I actually did practice that several times out loud to make sure that I could actually utter it tonight. Tonight's lecture is entitled The Atom, a Subtle and Fruitful Idea. I would also say that it's being given by a subtle and fruitful teacher. Welcome, Fred Schubert.
First, let me see, is the mic working? Yeah, I can't tell from you. I did want to speak about the atom, and there are a couple of points I'd like to make, just generally before we start, is that a few things here will point out the limitations of the Whig picture of history, where you discover something and then somebody just improves it a little and improves it a little, and we're ever onward, going upward and better. In real life, that is not what happens. It's the way I was taught a lot of this stuff, so in some ways I'll point out things that I only learned much later on in teaching. I have to always begin with the Greeks here. Phil, I think, might be a little angry if I didn't start out this way. But we've got our first kind of picture of the universe and its composition. The four elements, earth, air, fire, and water of the ancient Greeks, which are presented as well in the universe. Here's earth. We can't see the little layer of water around it. Then there's air, and then finally this upper layer of fire, and then all the objects in the sky. And many things could be explained with this picture of the universe, but it was a qualitative picture, and that was the emphasis on most of the Greek work. And let's see, let me go on, just to a couple of comments here. Democritus is one of the Greeks who worried about the problems of atoms. The question of the four elements making things up was related to a general question, which was, if you had an infinitely sharp knife and you took a sample of something and cut it in half and cut it in half and cut it in half, would you go on forever? In other words, could you cut forever and ever? And there was some who thought that would be the case, that it would be continuous, and there were many debates about this. Democritus was someone who thought there were atoms at the end. In other words, eventually you would cut, and then finally you'd come to the individual unit of things. And he felt, after much philosophical work, that all we really had were atoms in the void. And but at the same time, in a very Greek way, he questioned this view, because all he had were his very unreliable senses to give him this information. You know, his sight, which could be fooled, and hearing, and all of his other senses. So that he said, you know, if I'm really not sure about my immediate sensory perceptions, then how sure can I be that I know about the atoms in the void and that I know anything? And this was often a debate of among the Greeks here. Let me see if this. Over this way. Here we go. We have the Platonic solids, which were related to the elements. This is very interesting. We have these 5 regular solids, all with congruent sides, nice sides of identical length, and they were associated with the elements. Tetrahedron was associated with the element fire, because it just kind of has a lot of points, you know, so it might be a little burny. The icosahedron, which was the rolliest of the 5, was associated with water, which flows. The cube, I guess here, perhaps I can use my pointer. There we go. The cube was best for packing, so this would be Earth. You know, the Earth would tend to be made up of cubes. The octahedron was used for the atmosphere, to represent the atmosphere. I'm not sure why. And finally, the dodecahedron was left for all of those planets and stars up there in the firmament. And this was a view that was held. Now, the question comes up is, where are these guys getting this from? You know, is this the result of some big experiment? Not at all. It's really the result of thinking. If you think hard enough about something, and in a determined way, you ought to be able to come up with some idea of what's going on. And this is related to Plato's doctrine of recollections, which is really fascinating. The idea is that we are born, our soul, universal soul, contains all knowledge, and our endeavor through life is to recall that knowledge or parts of that knowledge. And learning is like that. The example I could give, I think that's a reasonable representation would be if you lost your umbrella and you think about it, what happened to my umbrella? And all of a sudden you go, the light bulb lights, and you say, oh, my umbrella, it's in the restaurant. You know, that's where I left it. So the idea is when you were in math class trying to understand the Pythagorean theorem, someone might have said, what are they talking about? And maybe the third time you looked at it, you said, oh, I get it. And a kind of a little realization comes. It's not a case that you went through a chain of givens and to prove like a geometric proof, but in fact you kind of have the light bulb go off. So he felt that these experiences were related. And similarly, we've got a problem. I have some quotes here from the Phaedo, which is the last dialogue in the sense that at the end of it, Socrates takes hemlock and dies, but he has a couple of hours left, and his friends are all distraught around him, you know, bordering on tears. And he's saying, but wait, we have a few more hours to philosophize. So we came up with a couple of things here. A philosopher can think profitably when he has got rid as far as he can of eyes and ears, the whole body, which is only a disturbing influence, which hinders the soul. In other words, when you're sitting around trying to reach new realizations and tap into your universal soul, your, the appetites and lusts of the body are just distractions. And finally, we have this. While we are in the body, while the soul is mingled with this mass of evil. Sounds very religious. A lot of the Catholic theology developed by Augustine in the 4th, 5th century really, you can see the Greek roots here, right here. This mass of evil. Our desire will not be satisfied, and that for the truth. So we could associate those solids with the elements because that's really what occurred to us. There's a famous anecdote of about 3 students in the Middle Ages. This thinking really held on for a long time, for pretty much a good part of 2,000 years. This point of view where we had it all inside of us, and observations and measurements in the outside world were not going to be helpful. And so 3 students are studying Aristotle's biology. They have handwritten copies of the book, and they come to the number of teeth in a horse's mouth. And they all have different numbers, 26, 28, 30. So they begin to debate, which is the best number of teeth that should be in a horse's mouth? And after this arguing for an hour or two, one of them says, you know, there are 4 horses out in the stable. We can go out and take a look. And of course, what do you mean? That's not the way to do this. That's exactly not the way to pursue this problem. So as an example of this point of view of things. Now, to completely switch, there's a wonderful scientist and historian, Jacob Bronowski, who did a series a long time ago on PBS and that, talking about the ascent of man. And he made the point, we're trying to get to understand atoms, and he feels that as we developed our abilities to shape the macro world, the large world, we began to kind of expand our consciousness enough that we would have the equipment to finally understand the micro world and look at this problem in what might be called a sensible way. We have these wonderful, complex things, which eventually, I would just like to, this is a little parenthetical aside, which we can kind of relate to modern things. Here's York Minster's flying buttresses, and here's an actual picture of a diamond that we have today. You know, looking down at diamond crystal, we have things that are not, you know, necessarily so different. Here's a famous old hexagonal tiles. I don't know how old they are, how many thousands of years. But what we found as we studied graphite, modern study of graphite, shows that it really is layers of hexagons. The green is empty. It's just there to show you markers that are very tightly held together. But these layers, in between the layers, there's almost no connection at all. They're very loose. So that if you have a pencil, graphite's the lead in a pencil, if you have a pencil and write the letter X, you go like this. And at that point, this layer here would be left behind on the paper. In other words, it would be swept away. This connection is very weak. And so you've got the black mark on the paper, which is now made up of these very stable things and can be there for centuries, really. Now, when you do the other half of the X, you may lose the second layer of graphite. So your pencil gets worn away. You have to sharpen it. You know, back from elementary school, we certainly all remember that. But we have this hexagon. We'll come back to this hexagon in the end. I'll make the point now that we have enough tools with us that we can actually start to bend this hexagon around a little bit. And I can show you in the next slide. Here we've got on the left, of course, the Great Wall of China. If you look at this fundamentally, it's a flat structure. If you look at one of these little layers, everything is kind of lined up. But by just cheating a little bit, we can make these beautiful curves, utilitarian, a combination of utility and beauty, I'm not sure just which is which. And our hexagons in graphite, it turns out we can turn them around as well and tie them tight. And we make what we call today nanotubes, which are the strongest materials that have ever been made, much stronger than steel, pound for pound, and they'll have effects on life as time goes by. So these examples are simply this relationship that Granovsky said that our ability to manipulate the macro world really helped us, I think, in trying to understand the micro world here. I have to stop off a little for Galileo because he gives us a big contrast to the Greeks. He wants to look without to figure things out. You know, let's look in the outside world. I don't feel obliged to believe that the God that gave me sense, reason, and intellect has intended us to forgo their use. And I think that discussing natural problems don't begin with the scriptures, but with experiments and demonstrations. And nothing physical, which sense experience sets before our eyes, should be ruled, let's see, certainly much less condemned, called into question, much less condemned. Galileo is a very modern writer. His books, there are a number of his books that are still in print. And it's remarkably refreshing to read it, but it also means something else. It means that we've kind of been hoodwinked a little bit by Galileo and Newton together, that we kind of think. Modern people think, in some ways we think like the Greeks, really, with that body-mind dichotomy. We believe that, we have it. But we also, this says, gee, this looks pretty modern. And it's mainly, Galileo was a great guy to move things forward. Okay, we have to leave Galileo with his arguments with the church and just go on. We just want to look at atoms. By the way, Galileo had some thoughts about atoms, but he kept quiet about it because the church got a little upset because in the Mass, the bread and wine are converted into the body and blood of Christ, and called transubstantiation. And if you saw the world as being made of atoms, it got to be a little unclear as to just how, you know, the atoms changed from the bread and wine atoms to the body and blood atoms, at least to 16th century church members or 17th century church members. So he kept quiet. He got in enough trouble with the planets here. All right, Newton said, of course, Newton rationalized the motion of the planets by describing the forces that operated between them, and really did change the world. One of the most remarkable things to me was to discover that after Newton's work got disseminated, the number of people killed for witchcraft basically fell to zero in Europe, because the notion that there was some sense to the world. You know, previous to this, that if a leaf fell from a tree, it might mean that I'm going to be sick tomorrow, or someone in my family may pass away. But the fact that there was some kind of systematic quality to it did change the view of many people here. Now, he said that, look, in the same way as I study the planets, if I knew the properties of atoms, I could describe them and the behaviors we see there. But he did a hypothetical calculation, and just kind of a seat of the pants thing, what if, pure speculation, and got some decent results. And Dalton, who is not Newton by any means in terms of scientific ability, completely misread this 100 years later. And he thought that Newton had absolutely proved that atoms were at the nature of things. So he went on to develop his atomic theory. And here's Newton, he's a Quaker, very reserved man, quiet man. They said kind of like a boring character, really. Not, the one thing we know about him is that every day he went out and took weather measurements in his neighborhood for 57 years. And those measurements were kept by the officials at Manchester for a long time, until I think there was a bombing in the Second World War or something, and they finally lost them all. But he suggested that there were atoms, and he reached a number of conclusions as a result of this that made him into kind of a superstar. When he died, 40,000 people came to his funeral in the city of Manchester. There were probably maybe 100 who understood what he had done. But yet, you know, the idea that the world was made of atoms, and we knew it, was a big deal. Now, I don't have all his premises here with his theory, but let me just give you a few here. Matter is made up of indivisible, indestructible atoms. Here are Dalton's actual models, you know, that he used. And compounds are formed by combination of those. If this is a C and this is an O, this could be CO2, like carbon dioxide. Or if this is an oxygen, then the H's stand for hydrogen. It would be H2O. He didn't have our modern symbols. They didn't come for a few more years. But he said, look, if what I say is true, then the composition of water should be the same all over the world. If you find in England that by weight 1 part of hydrogen reacts with 8 parts of oxygen to make water, then that should be true in China. It should be true in the Americas. This was new stuff, really, in a way. People weren't that sure. And in fact, this and a number of other suggestions he made really had atoms catch on. Now I have this is an unusual trend. This is the only graph, I promise there'll be no more graph. This is from this great thing Google has called the Ngram Viewer. And what they've done is they've read in 5 million books, and they have, you can go and search the frequency of any word, see how often it actually occurs. And what I did was look at this is when Dalton suggested his theory, and this is 1850 here. So in all the publications that they could find, we find that atoms really take off. You know, Dalton's really caught on. It's really the big thing. And you think this is the way, with the Whig theory, this should go on forever. But all of a sudden, around 1830, they began to say, well, wait a minute, you know? Wait a minute, this is not so obvious. And atoms kind of fell out of favor, which is maybe a little surprising to some of us. So let me go back and see why. They looked at what Dalton said, and they said, look, who's Dalton saying matter's made up of indivisible and indestructible? He doesn't know anything about that. He's just postulating this stuff. And they finally said, they took what's called a positivist attitude. And this is something I hope maybe I can explain this, where you take relationships, but don't read into them deeper meanings. So the people were happy to use Dalton's 1 part to 8 part, but they said that doesn't mean there are really atoms. All it means is that 1 part reacts with 8 parts. And so essentially, atoms did fall out of favor for quite a while. Now, one thing they did do for some simple compounds, which were related to what Dalton had done, was to write drawings here. And I'd like to see, these are some nice simple molecules. And the idea is that we find that these are not molecules. So let me just see if I can't show you. Here's a novel. This is a relationship diagram in a novel. These are all the characters. And I don't know what these things mean. I got this, I can refer you to the website for this. And if you study the novel and all the relationships among the people, you should be able to explain their behavior. However, if you miss one, let's say you don't know that this guy secretly meets, you know, this woman over here and they haven't told us that, you would have a picture that did not explain everything. So this is, you've got to look at this almost in this way. These are not as interesting as people, but they found that carbon tended to always bonded with 4 hydrogens, so they would, I shouldn't even use the word bond. It was associated with 4 hydrogens. it was only oxygen was associated with 2. So when they got together, we get our old friend CO2, where there are 2 relationships oxygen can form, and there are 2 relationships here. So that's it. This is it. There's nothing more, no intrigues, nothing sinister. But yet many things could not be explained. Like 99% of all the materials in the world could not be explained. So what happened in science, so back to our diagram here, what happened in science, 2 things. One was we had people who were involved in other fields. One was a linguist. I don't have his picture here because I don't have time to do it. But he came upon all these strange chemical formulas, and he was trying to understand how we could rationalize them. And he treated it like a foreign language, like hieroglyphics, trying to translate hieroglyphics. And he developed a really excellent system that managed to describe many compounds of fair complexity. Unfortunately, his stuff wasn't published in a timely manner. He had a nervous breakdown, and he kind of disappeared from the scene. But I was Cowper, C-O-U-P-E-R. I think if you were not an Englishman, we wouldn't know him at all. But the English tend to kind of, keep track of their people. We had another man. This Kekulé, as a young man, was destined to be an architect. Apparently, he showed some great talent along those lines as a child. And he was sent off to school, but he had to take a science elective. It's one of those things. I've got some seniors here who are going to be faced with this problem. But there's a wonderful thing going on in German universities. The best chemist had to teach the freshman course. And so Justin Liebig, who was the best chemist in the world at the time, taught this course, and Kekulé's eyes are open. How can we solve this mystery? He brought up, we don't know how to lay out the diagrams that describe our the compounds. We're making a lot of compounds, but we can't put it all together. Well, he had a number of dreams that affected chemistry, but the key one was he was sitting before the fire, fell asleep, began to dream of snakes. And in this dream, one of the heads, the head of a snake, bit its own tail. And he woke up and said, that's what's missing, and it's the rings. He introduced the whole idea of rings. And suddenly, thousands of compounds, literally, whose properties could not be explained, were explained. And he did much other work in chemistry too. This is a slightly more modern version, but this Kekulé still had this stilted. Remember, we're doing relationship diagrams. He doesn't necessarily believe in these things, and let's see what his comments are. He actually has a few. He said, look, whether atoms exist or not, it doesn't really matter that much to me. It's a philosophy question, okay? So I don't believe in the actual existence of atoms, taking the world and the literal significance of individual particles of matter. And yet, as a chemist, I have to assume there are atoms, or I can't move ahead. So, what does this guy mean? This would be like a politician you'd kind of put on the carpet for this. But there was this general ambivalence towards jumping ahead to atoms, this positivist view. We accept the relationships, but we don't really know what they ultimately mean in the end. 15 years later, another scientist, Van Hoof, suggested that rather than use these simple relationship diagrams, let's just accept that the atoms really do occupy three-dimensional space and that they're really there. And he came up with this old Platonic figure, the tetrahedron, to describe this, what we used to describe this way. He said, look, the world's three-dimensional. I can see it. I'm not a flat thing on a piece of paper in flat land like on the left. We go into 3 dimensions. These are some of the models that he made. These are up at Yale right now from around 1900 or so. And he was able to explain a lot. However, he met tremendous resistance. And here, I just have this one comment. He is the most famous organic chemist alive at the time here, talking about these 3-dimensional pictures here. This philosophy, which has been set aside by exact science, is dragged out by pseudoscientists from the junk room, which harbors the failings of the human mind, dressed up and rouged freshly like a whore to try to smuggle into polite society. I mean, Rush Limbaugh wouldn't talk. And yet, so the resistance was tremendous, but there were quite a few things that were explained, and eventually the day was won by this. Now, something happens immediately. This little bit of chemistry we now know. Here are some tetrahedral shapes. They're kind of like that picture, but not beautiful. But an interesting thing was observed was that if you happen to have a molecule that was complicated, and let me tell you, all the molecules of life are complicated. The simplest bacterium is loaded with molecules with hundreds and thousands of atoms. And if they're the least bit complicated, what we discover is that the mirror image is not the same. this is an object, there's its mirror image. I think you can kind of see the reflection. And someone says, well, they look like they're the same, but if you rotate this around, so the reds and the greens line up, the blues and the yellows don't line up. You can do this afterwards, if you know. No, I'm serious. I have 3 of them set up. But in fact, it really does make a tremendous difference. And what we find, and this is the big jump, which is something to think about, is that all life on Earth is complicated enough that the mirror images of the key molecules are different from one another. And what we find is that all life on Earth is left-handed. From the simplest bacterium to the elephant, they all share this left-handedness. Now, left is arbitrary. I couldn't say right-handed, but I happen to be lefty, so I'll. There's another reason too. But this is a little strange. You know, it used to be. I used to think of this. Well, if the conditions are like they are on Earth, with oxygen and reasonable temperature and materials around, that life should spring up. The feeling is life should be everywhere. And if that were the case, and say life started 10, 20 times on Earth, we ought to have 10 left-handed kinds of organisms and 10 right-handed kinds of organisms. But we only have the left-handed ones, which makes things a little bit more lonely here, actually, if you think about this. That we only, and it implies, at least in part, that life only started once, or only a few times. You could have 2 or 3 left-handed sets of molecules starting off, but it all has to do, again, that once the molecules get complicated, mirror images, it's like gloves. Left-handed glove and right-handed glove are not the same. And like right now, whoops, I don't have a lapel pocket, but I have a horse here, so that my mirror image would not be the same. Oh, here's my lapel pocket. So I would not be the same. So anything that's the least bit complicated, and the living things are like this. I'm trying to, this is a representation here to try to show that, but there are some other ways to explain this, but it really is a little bit of an unsettling aspect here. Just to show you, here's a familiar mirror image pair. These 2 molecules are really the same. They have the same number of atoms. They have all these properties we talk about. They boil and melt at the same temperature. And yet, we sense them differently. This is caraway seed, the taste of caraway, and this is spearmint, because our tongue is full of all these molecules that tend to favor one mirror image of the other, so that these 2, the mirror images are not identical, the little asterisk shows you the place where they're different. In fact, they will be different, so we'll sense them. It's like vitamin C. If you take left-handed vitamin C, you don't get scurvy, everything's fine. If you were to take right-handed vitamin C, absolutely useless as far as vitamin is concerned. You know, some of us are old enough to remember thalidomide, which was a drug. It turned out that one mirror image alleviated some difficulties and symptoms during pregnancy, and the other one caused birth defects, unfortunately. And what the medicine that was given out mixed the 2 of them together. And so that's, again, a long time ago here. Francis Crick, one of the discoverers of DNA, felt that the more he looked at life and the more he understood it, nobody understood the basic molecules of life any better than he. He's an honest man with all the knowledge available to us. The origin of life appears almost a miracle. So many conditions that would have to have been satisfied to get going. One of his theories was he advocated panspermia. He felt that life was planted here, perhaps by intelligent organisms. You know, they might, some Captain Kirk 3 billion years ago, no, came by, dropped the basic stuff here and said, well, let's see what happens. And then his great grandson came back in another ship, looked over how things were and said, well, it didn't work out too well here. So we won't see so many visitors as we might have from space. But it is really remarkable that we do have life itself. Here are the boys, Crick and Watson. They actually made this molecular model, 1,000,000 to 1 of DNA. And they used it, first of all, to try to see how things fit together, to actually work out their structure, and then to convince their fellow scientists. The models had become so important by this time. I want to, let's see. I have here a little DNA segment. Please don't get upset by all this stuff. The colors are all that matter. The purple is the T. What we find is that in the DNA, there are 4 code letters, which we'll just call C, G, T, and A. And some of the work, by the way, that they did do with models was, and this was the big aha moment for Watson. He actually had a picture of these 2 molecules, and he was working kind of in the middle of the night and realized if you put them together, they fit perfectly. And that these 2 tended to complement one another, and they always do. So we've got our 4 code letters, and we're going to abandon all these molecules, but let's say give a little deference to Kekule. See all the rings we have here? The rings are definitely in the middle of many stable molecules here. Here's just to show you the way this genetic code works, and with what I consider to be an interesting case. Normal hemoglobin, here's some of the code letters. There are many. Now, the human genome has about 3 billion of these code letters. Well, we just want to look at a little area here for the formation of hemoglobin. This little section, that all the 4 letters are CTG, turns out 3 letters make up one bit of code that tells, essentially, gives you the formula for which amino acid you want to prepare. So CTG was right, here we go across. But someone can be born with a mutation where this A letter is replaced by a T. A lot of reasons this could occur. One is just background radiation. There are many other things. Thousands of years ago, this happened. So there was a little difference. In other words, normal hemoglobin, mutant hemoglobin. And they're almost identical. Here's this big mess here is a hemoglobin molecule. And here, these 2 red marks are the bad mutation that we have. That's the problem. And essentially, this is the salad dressing problem, if I could put it this way. We know that if you let salad dressing sit, the oil and water settle. Now, it happens that in the mutant form, with that little red, these CH3s, they characterize the chains that we see in oils. Oils tend to have these. On the other hand, things that dissolve in water, like the vinegar, tend to have this other group. So what happens here, this is a bit less soluble in water than it really should be. So if we take a look at some red blood cells, these are the normal red blood cells, the Bialy shape. As long as we're in New York, we could say that. I guess we probably have to give it another name here. And as long as the chemicals are in reasonable concentrations in there, these are good oxygen carriers. But a little shock to the system, a little imbalance in concentrations, in that mutant one that we looked at, the hemoglobin can start to crystallize out. And when the hemoglobin crystallizes out, we actually get the sickling of the cell. It's very much like if you're at a puddle of cold water on an ice cold day, you see the ice begin to form. And once that happens, this is now useless. Removed by the spleen, everything would be okay, but if this is a representative sample and 1/4 of your red blood cells aren't working, if this happened in an instant, you'd suddenly be kind of like gasping for breath. If this happened in a chronic way, you would be suffering fatigue and stuff all the time. And you might be more prone, more prone to any kind of altitude sickness. So that one, the key point here is this one little molecule. That change is the source of all this. Now, it's interesting in a way, but in the future, at some time, it'll be 20 years, 50 years, perhaps we can address that problem and help people with this condition. One other mutation I'd like to one code letter off. This is a story that you probably know, so I'll just mention it briefly. Queen Victoria was a mutation. One of her code letters was off. And the code letter was off on the gene for blood clotting. So that what happened was all of her offspring, down through the generations, are potentially prone to hemophilia. Only the males get it. And I can't go through all the XY stuff, but let's just say that that's true. The women can be carriers, but the men get the disease. So Queen Victoria had it. So since blue bloods tended to marry one another, the hemophilia spread from her to the royal family in Spain, in Prussia, of course in England itself, and finally in Russia, the story that we probably all know pretty well. This is one of Victoria's granddaughters, Alex, I think her name actually was, and she was a carrier. She had 4 normal daughters, the 4 girls we probably do know, and they had 1 son who did have hemophilia. Now this was a real disaster. Of course, in Russia, the crown has to be inherited by a male, can't be a female. So this hemophiliac son, whom they knew was not going to live that long, was their only hope for the Romanov dynasty, the immediate family, to go on. Now, the mother was distraught over this. This is part of the reason she became involved with Rasputin. Apparently, when he was around, there were fewer episodes of bleeding for the son. And of course, the Tsar, this is part of the reason he took his eye off the ball here. You know, when you're the Tsar and you're preparing the country for your son to inherit, you're focused. But if you know that there's not much hope. I mean, one of the most poignant stories for me is when these when the people were taken to where they were all killed, that at 14, strapping kid, he had to be carried there by the Tsar for his last, his last meeting. So again, this is one molecule out of place, and not only did it affect people immediately, but it also had earth-shaking effects as far as the political world is concerned. Let's see, let me just say a little about molecular relatives. Here's some more of those code letters. And I've got 5 species here, and we can look at this. It's just one section of the same gene for 5 different species. The first one here is the human, the set of letters for this area, and then we've got this other, our closest relative, at least in this bunch, who's the chimp. The chimp has the same ones. We share about 98% of the letters with the chimp. So he's different from us for sure, but not as different. Here we've got, so we feel the chimp separated from us about 7 million years ago, so, from an evolutionary point of view. Now we have a slightly more distant relative, the baboon, who does show one difference here, and in fact, he separated at some time longer in the past than that. We have these 2 guys, fortunately, that aren't close relatives, the rat and the mouse, and it's borne out here that we are different from them. Now I'm presenting this to you, the way it's really done. It used to be that evolutionary work was done, well, tigers look like leopards, and so they must be related morphologically, we worked on. Nowadays, if a species exists, the way you see how closely related it is to another species is to look on the genome. And that really, essentially biology has been turned into molecular biology. Much of the macrobiology has been turned into that. You could also, by the way, I can present this example as kind of an SVU problem. Who's related to whom. By the way, the Tsar and his family, I forgot to mention, they actually were involved. DNA analysis is what verified that they had actually unearthed the bodies of the Tsar and his family in the 1990s. And one way that they were sure it was the Tsar, someone had tried to assassinate him in the late 1800s, and they had saved the blood-stained shirt that he wore. So they took a sample of the DNA from that, and by amplification, were able to match it to the DNA in the body on Earth in Katerinburg. I want to finish up by just saying that Plato does live on here. We kind of gave the Greek short shrift here in the beginning, but there is this belief, scientists today, operating today, that if you have conflicting theories that are trying to explain something, that usually the more beautiful will be the correct one. And it is kind of well, what do you believe then? Well, you just come to believe it. And it is a Greek type of thinking. As human beings, I think we have thought experiments like Einstein, where he travels along on a light wave. They revealed great insights, and they moved science forward. Well, they weren't, strictly speaking, experiments. I mean, Einstein took cognizance of all the experimental results available, but he still let his imagination run wild here, and that's what allowed things to move ahead. Science makes its largest leaps when intuition steps in to aid rigor. There's this view, especially outside science, that it goes like this. Hypothesis, experiment, results, hypothesis, experiment, results, hypothesis, experiment, results. This is just not true. That doesn't happen in science. Maybe some well-developed corner where you're just mopping up, yes. But if you're going to change the world and change things, the imagination has to step in. And this whole notion of intuition, is it really akin to being in touch with Plato's universal soul? Perhaps you can think about that. I would just like to mention Einstein once more to finish up, because in some ways it's very sad, but it also is edifying too. The beginning of the 20th century, he really began this revolution in atomic science. But as things developed, we found the atomic world is very probabilistic at its heart. And he found this very troubling. He just really did. He just struggled with it. In fact, he understood so much more than the rest of the people the horrible implications of this. Things like spooky action at a distance. People are studying right now today. Turns out to be true. Einstein couldn't believe it would ever be true, but we know it is. And the fact that cause and effect on the atomic level kind of disappears. He finally said, he and Bohr used to argue about this, God does not play dice with the universe. Now, he and Bohr actually debated these issues for about 20 years. And Bohr's final answer to Einstein saying again about God would not do this. Bohr said, Einstein, who are you to tell God what to do? And there is no right answer to that. I will stop now. I have a few more examples, but I think that's enough here. Whirlwind tour here. Thank you very much. Try to answer a question or two. I don't know.
Let's have a question or two if there are any. Thank you, Fred.
Oh, yes.
Is history repeating itself with the discoveries being made in nanoscience and nanotechnology? In that the discoveries are being made by people who dream and refuted by skeptics?
I think that element is there. That whenever you do step into a new area, that's always going to be true. And I think, in some ways, look, I don't have the answer to this, but I think partly just there's something about being a human being alive that assuming you're in reasonably good health, you have this sense that in some ways you do feel godlike, really. You know, not when you're being online in the motor vehicle bureau or something, but if you're sitting somewhere and able to contemplate the mysteries of the ages, that you do have the sense that somehow I'm important and somehow what I have to say matters. And I think that kind of does lead you to think that you can offer something. Yes, yes.
I have a question. You were talking about the left and the right.
Yes.
Fitting like a glove, maybe. Is there, and also DNA, is there a relationship to left and right hemisphere, you know, the whole
in the brain?
idea in the brain, and also the whole idea of symmetry, because in terms of symmetry, left and right are a reflection of each other, but in terms of balance, I don't know how to ask the question. It's just, as you were talking, I was getting these ideas.
But the answer I'd say is no about the brain, brain stuff. I'm kind of an anti-left-right brain thing, because as time goes on, we find that the studies find that more and more happens that we in both sides.
Right.
Fortunately for us, you know, if you suffer some brain damage, that you can recover. You know. Yes.
It's just how do you define symmetry? I mean, I understand the difference between left and right, but how do you define what's left-handed? I mean, because you have
that is arbitrary. But the reason, by the way, I say left-handed is that one of the ways they have of separating these two is if you, I didn't want to say this, if you shine polarized light through a sample of one mirror image, the light is bent to the left. And we call that levorotatory. And that's nominally left-handed in most of our natural molecules. Whereas if you take the right-hand mirror image, it tends to rotate the plane of the polarized light to the right.
So that's the standard.
That's right. Okay. That's a test that was known even, in fact, Pasteur was the first person, even though he was long before models, he was the first person to realize that this is what was going on. He, I can't, if I could talk about that, but I wouldn't be able to answer to a question. But, thank you very much.